Welcome back. So in the last few lectures, we have seen how to use recurrence relations to model various counting problems. Now, as we have told, recurrence relations are a very essential part of mathematics, or particularly in counting. So in fact, a recurrence relation is an equation that recursively defines a sequence or a multidimensional array of values where there are some initial terms and the nth term is defined as a function of the preceding terms. Recurrence relations is extensively used for combinatorics, analysis of algorithms, in computational biology, in theoretical economics, and many other subjects. So we have already seen some of the recurrence relations, and we have seen how recurrence relations can be used to model various problems, particularly combinatorics problems. But we have not seen how to solve recurrence relations. In this video, we will be focusing on how to solve recurrence relations. So here are some of the recurrence relations that do appear in real life problems. So first one, say t1 equals to 1 and tn equals to 2 plus tn minus 1. The second one, say t1 equals to 1, t2 equals to 2 and tn is equals to tn minus 1 plus tn minus 2. Or this one is what we got from the Tower of Hanoi problem, where h1 equals to 1, h2 equals to 2 and hn equals to 2 times hn minus 1 plus 1. This one is basically what we have the Fibonacci series, where f1 equals to 1, f2 equals to 1 and fn equals to fn minus 1 plus fn minus 2. This is what is known as the Fibonacci series. It's quite a famous series that that appears again and again in real life. Then we have this one, b1 equals to 1 and bn equals to bn over 2 plus 1. Then we have m1 equals to 1 and mn equals to 2 times mn over 2 plus n. So these two appears in various algorithms, particularly the binary search algorithm and the merge sort algorithm that are very popular in the algorithms literature. And then we have a slightly more complicated one, c1 equals to 1 and cn plus 1 is equals to summation of I equals to 1 to 0 to n ci cn minus I. Now, for all of them, we have to now understand how one can solve them. So, what is the technique for solving any of these recurrences? Right? So, how to solve these recurrences? Now, the first technique that we are going to look at is the simple thing of guess the solution and prove using induction. In this video, we will see how this technique is useful, and then we will, in the next video, we will see how one can guess the solution. So say here we have this example, t1 equals to 1, tn equals to 2 plus tn minus 1. Now, how do you solve this particular problem? Now, first of all, if somehow magically you can guess this number, then we are great. Say for example, if I tell you that guess that tn equals to 2n minus 1. Now, if this is the guess that we make, then we can try to prove this statement using induction. So the technique is first guess and then prove by induction. Now I have skipped a big chunk of how to guess this number. We will see that one, see the technique of guessing in the next video as well as in the next whole week. Guessing the solution for the recurrence relation is possibly the most challenging part of solving the recurrence relation. But in this video, we will be focusing on how to solve the guess if we have the induction. If we have the guess right. If we guess the thing right, how do you prove it? Right? So, how do we prove by induction? Now, if you remember, so we should have a base case. In this case, base case is say n equals to 1, and we have okay t1 is equals to 1. This is something that is given, and which is of course same as t2 times 1 minus 1, right? So this value is correct for t1, right? And now we have the induction hypothesis. Induction hypothesis, which says that say for some n, Tn equals to 2 times n minus 1. And in that case, what is the inductive step? Inductive step is to prove the same statement for t of n plus 1, which is 2 times n plus 1 minus 1, which is 2n plus 1. Now, how do we prove it? Now, of course, by the thing that has been given to us, t of n plus 1 equals to 2 times 2 plus t of n, right? Which is equals to 2 plus 2n minus 1 by the, so this is by induction hypothesis, which is equals to, of course, 2n plus 1. And that is what we had to prove, right? Hence, we are done. Hence, we have proved the inductive step. That means Tn equals to 2n minus 1, which is for all n greater than or equal to 1. Right? So this is the proof by induction for how once we have the guess right. Correct? So let's go over the next one. One more example say. So this example 2 says that t1 equals to 1 and tn equals to n plus tn minus 1. Again, first of all, you have to guess it, and let's imagine that somebody just comes up and manages to guess it correctly, and says somebody comes up says that tn equals to n into n plus 1 by 2. Now, once someone has guessed it, we have to prove it. We have to ensure that the guess is right. And to get it true, we have to again use induction. So like in the earlier case, we have to again prove this one by induction. And let's see how do we prove it again. The base case, n equals to 1. Of course, t1 equals to 1, which is 1 times 1 plus 1 by 2, right? Which is what, so the thing is correct for the case, or the case n equals to 1. Now we have the induction hypothesis. What is this? Says that Tn equals to Tn equals to n into n plus 1 by 2. Now in inductive step, we have to prove that t of n plus 1 equals to n plus 1 into n plus 2 by 2. Now how do we prove it? Now t of n plus 1 is been given as n plus tn minus 1, which is n plus n into n plus 1 by 2. This is by induction hypothesis, which is, if I take the sorry, I made a mistake here. This is not n, this should be n plus 1, right? So this is also, this is because tn equals to n plus tn minus 1, so tn plus 1 has to be n plus 1 plus tn, and this is equals to n plus 1 plus the given induction hypothesis, which is n into n plus 1 by 2. So now I can take n plus 1 common. In that case I get 1 plus n by 2. So this is 2 plus n by 2, which is of course n plus 1 into n plus 2 by 2, which is what we had to prove. Right. So we have t of n equals to n into n plus 1 by 2 for all n greater than or equal to 1. Again, the idea is simple. If you can guess the value correctly for Tn, then you can prove what Tn is by induction. Right? So let us see one more example. What can be the various guesses? So this is the tower of Hanoi problem, right? So T1, H1 equals to 1 and Hn equals to 1 plus Hn minus 1. Again, we first have to guess it. Now what is the guess here? So the guess is Hn equals to 2 power n minus 1. And again we have to prove this one by induction. Note here that if we guess it wrong, we will not be able to prove it by induction, or we will not be able to prove it, period. So thus, only if we guess it right, we will be able to prove this statement. So there are people who actually come up with these guesses by some various intuitions of their brain, and there are some techniques also which will help to come up with the correct guesses, which we will study in the next few lectures. But again, for this particular problem, how do we prove this statement? Again, we have to look at the base case. So base case n equals to 1. So here h1 equals to 1, which is 2 power 1 minus 1, which is 1, which is right. So the base case is correct. So induction hypothesis, say Hn equals to 2 power n minus 1. Inductive state. So we have to prove. So to prove h of n plus 1 equals to 2 power n plus 1 minus 1. Now let's see. Hn equals to, h of n plus 1 equals to, by what is given is 2 times hn, which is 1 plus 2 times 2 power n minus 1. This is again by induction hypothesis, which is 1 plus 2 times n plus 1 minus 2, which is 2 times n plus 1 minus 1, and this is what we had to prove. So h of n equals to 2 power n minus 1 for all n greater than or equal to 1. Note that this is not only a way to proving the recurrence, this also, if you go back to your previous video, this gives us a compact form for the number of moves required for the Tower of Hanoi problem. So the Tower of Hanoi problem therefore requires 2 power n minus 1 moves, and we got it by first modeling it as a recurrence relation and then solving the recurrence relation. Now, how did we solve the recurrence relation? We first guessed the recurrence relation and then we proved that the guess is right. So this is how most of the counting problems work. You first model it as a recurrence relation and then you solve the recurrence relation. But all this is fine if you can guess the recurrence relations correctly. You first guess the recurrence relation and then prove it using induction. The main question is, how do you guess the solution? And we will be doing this problem of how to guessing the solution to the recurrence relation in the next video. We will see one of the techniques, and in the next few videos we will see the other techniques. Thank you.